Hello and welcome. I am Dr. Will Weber from Whatcom Community College, and this is the video version of a talk I'm giving at the Washington State Community College Math Conference in Wenatchee, Washington in early May. And here's all the information, right? My email. The materials that you'll see here are all available on a public-facing WAMAP page, and I'd like to point out that this is ID number 268. I am still using a 3-digit WAMAP course. Anyway, there's the video. This video will be posted on YouTube, and the link will be here. Of course, I haven't finished the video yet because I'm making it right now. But if you're at the conference watching this video, no. If you're at the conference listening to me talk, the video will already be made, and the link will be written here. So let's take a look. Is the speed of darkness faster than the speed of light? Now this all started back. This whole thing for me started back years ago. I want to say 1980-ish, would say when it was. I was high school, and it was evening, after dinner, I guess. I had gone up to the store to buy a couple of gallons of milk, and I was walking back with the milk in my hands, and it was wintertime, and it was snowing. And it was one of those snows where there's no wind blowing. Each snowball has got to be, golf ball sized or bigger. And the light is just reflecting everywhere. It's just absolutely magical. I love this type of snowfall. And so I'm just walking home, just sort of looking around, absorbing all the beauty. And all of a sudden, I'm just about to get home, and it feels like the ground is just rushing in at me. Just, I had no idea what was going on. So I stopped and took a look around, and I realized what was happening is that every single snowflake was falling and casting a shadow. The street light that I was walking underneath. Did I mention I was walking under a street light? I was walking under a street light. Yes, and the snowflake, the light from the street light would hit the snowflake, of course, be blocked by the snowflake, and then there would be a shadow on the ground. And these shadows were coming screaming in from infinity, or just moving really fast and then slowing down just as the snowflake would land on it. Just like this, actually. Let's get my face out of the way here. If I set this in motion, you can see that snowflake fall. The streetlight's right there, and the shadow's right here. It's just coming in. It slows down. It slows down, and finally the snowflake lands on it. Right, and then here it comes. Wow! You can see it zipping right in there from the right side of the screen all the way down in, and then the very last bit just moves so slow. And of course, this was happening not just with one snowflake, but with all the snowflakes around. So there was this whole radial pattern out in front of me, just all around the light of these snowflakes, just zipping in. In fact, let me show you what it was kind of like. The best I can do with Desmos here. So come on now. We got a little Desmos 3D. Get my face out of the way again. And let me zoom out a little bit here. How do I zoom out? There we go. So if we look down at this, you can see each of these shadows on the ground come moving in. Some of them seem to be moving faster than others, but the really fast moving ones are trying to get to snowflakes that are going to land in the middle there. And this was the sensation I got. In this animation, the light is up at 4, so the street light is just up here, and the snow is just gently falling. And each one, if you focus on, let's say, one shadow, whoa, what's happening here? If you focus on one shadow, that's that fast-moving one going in there, it'll move in, and then eventually, I'm looking at that shadow right there, eventually a snowflake will land on it right there and disappear, right? Every single snowflake is doing that, making that shadow, and this was just, it was fascinating. Anyway, at the time, I was, maybe a sophomore or junior in high school, and I didn't really know calculus. But once we got to calculus, and all of a sudden I realized I could, I need to, let's see. I could figure this out now. Man, my face just keeps getting in the way. Related rate problems, right? Once we start learning related rate problems, I realized that, if I know the speed at which this is falling, and I'm assuming terminal velocity, right? They're big, fluffy snowflakes. They're falling at a constant speed. And then I can set up the geometry here, and I can say, all right, call that length S. And if I know dHdt, I ought to be able to calculate dsdt and figure out how fast that snowflake is moving. And I really wanted to see that, yes, it is indeed moving very fast to begin with, and then slowing down as it got closer to me. So, just like any other related rate problem, they're all the same. Related rate problems, they give you one rate, they ask for another. So here's the rate that I know. dHdt is, I'm just pulling a number out of the air here, literally. Minus 1, falling at like 1 foot per second or something like that. I want to know how fast the shadow's moving. So dsdt is equal to what at any particular height? Usually in a Calc 1 problem, they'd give you a specific height to evaluate it at. But I just want to figure this out as a function of h. So what do? I need to find a relationship between my two variables, h and s, so that I can then implicitly differentiate to find the relationship between dHdt and dsdt. I need to relate the rates. So here we go. I'm looking at this, seeing some similar triangles. So vertical to horizontal on the small triangle there. H over s is 15 over, and I'm just pulling these numbers out of, just at random. 15-foot telephone pole, the snowflake's on the land 3 feet away from it. Anyway, whatever. And I set up like this. I could do it in more general, having a variable height here and a variable distance there, and get it as a function of everything. But this is sufficient for what I wanted to do. Technically, I could right here just start doing my implicit differentiation, but then I'd have to do two quotient rules. If I were doing this in a Calc 1 class, I would probably do this first. I'd multiply by both denominators to rewrite the equation this way, in which case then I'd be doing product rules. But for the purpose of what I want to do in this talk, I'm actually going to solve this for s because it's linear in s, and I can solve s explicitly as a function of h, and then I can just calculate dsdt is dsdh times dHdt, right? Chain rule there. And it's a quotient rule there, and I end up with plugging in that dHdt is minus 1, I get that dsdt is minus 45 over 15 minus h. It's quantity squared on the bottom there. And I notice a couple things. One, when h is 0, that is when the snowflake hits the ground, that we get dsdt is negative 1/5. This happens to be the reciprocal of the slope between the light and the point of contact, and I can prove in general that that's the speed of the snowflake as it hits it with any combination of distances there. But I noticed that as h is smaller, 15 minus h is bigger, and that's in the denominator. So smaller h's mean smaller speeds. Bigger h's, when h is closer to 15, this is getting smaller, and I'm dividing by a smaller number so that I would be getting bigger results. And so as h gets bigger, the speed is very high. So that, to me, it justified what I knew. It's like, it's what I saw. It was coming really fast when the snowflake was up high, and then it slowed down as it landed. But curious thing here is that this 15 minus h quantity squared in the denominator means that there is a vertical asymptote at 15. And that as the snowflake is just passing from 15 to a little bit lower, I'm assuming an infinitely long flat ground, and that shadow is zooming in from infinity and having to move arbitrarily fast. That is, you take h close enough to 15, you can make dsdt arbitrarily large. In fact, you can make it faster than the speed of light, which begs the question is, can that shadow move faster than the speed of light? And I think, well, shadow is just a little patch of darkness. So that begs the question, is the speed of darkness faster than the speed of light? And, of course, I went on to not just being in a Calc 1 class, but now I teach Calc 1. I've taught it a zillion times over the last 30 years. And I always ask my students, is the speed of darkness faster than the speed of light? Is this really what's going on? Can that thing go infinitely fast? What actually happens? And when they don't answer, they come back with the question of, well, what does happen? I say, ask your physics instructor. And I will admit that I have never had a physics instructor come to me and say, Will, you told your students to ask me a question, and either this is really simple, let me tell you what happens, or that's a really interesting question, I'm not sure, can we figure it out? Well, I've never had a physics instructor come to me and do that. So 30, 40 years later, I said, I should probably figure this out. And so over the last year, I've been poking around, analyzing this from different ways, and I'm pretty sure I got a pretty good idea of what actually happens and whether that shadow can move faster than light or not. So let's take a look at what I've done. Now, first of all, in the analysis, in trying to figure out how to analyze this, there was something about the shadow coming in from infinity that bothered me, and I would rather turn it around and have it go out. And so I'm thinking, either I run time backwards, or it's like, rather than a snowflake falling, let's think of a helium balloon or something that the kid lets go of, and it rises, right? And it's still going to rise at assume a constant rate, right? And then that can cast a shadow, so as it rises, the shadow will be going out, and that's just the same as running time backwards and whatever. But I felt better about having the balloon rising than just thinking about time going backwards and whatever. But then that reminded me of another classic related rate problem, and that's the searchlight problem, right? And so the searchlight problem is you have a lighthouse or something like that. So it's sending out a beam of light, and that beam, it's spinning around, and so the beam is rotating. And you've got, let's say, an infinitely long straight wall here that, as long as the beam is aimed towards the wall, you'll have a spot on the wall to look at. And as theta spins, let's assume it's going counterclockwise here, that S will move along the wall, right? So here's my face is probably going to be in the way. Yeah, of course it is. So the beam is in between the red, and the light is in between the red and the blue. And as I turn it on, you can see it spin around. And sure enough, the spot on the wall is going to come, it's going to come screaming in from infinity on this side, and it slows way down in the middle, and then it moves off really rapidly. And, from all of my intuition says, yeah, that's what happens. It comes in from infinity. In fact, it's big, and the spot gets smaller until in the middle here, the spot is as small as it's going to be, and then it grows in length and in speed, and it heads off that way, right? And, we can do this. Two different spotlight problems that I have looked at to analyze. There's this one, which is essentially a point source. So the light is coming from a point, and it's radiating outward in a triangle or a cone, depending on how many dimensions you want to put here. This is set up that I can move this and open the beam or close the beam. You can see there's an opening here that's going to let the light out, but no light is coming out of that circle elsewise, just right between the red and the blue. The red is the sort of the leading edge of it, and the blue is the trailing edge. So anyway, that's that. The other version I have of it is a spotlight, where I picture it as a beam of parallel light coming out. It's not spreading outwards. It's going straight. All light is parallel, but yet it's still the same thing. It rotates around, and the light is coming in from, the spot on the wall would have to be coming in from infinity on this side and heading out to infinity on that side. And typically when we do a problem like this in Calc 1, we never talk about what's happening on the coming in from infinity. We always look at it as, taken off in that direction. But still, when I do that related rate problem and I say, okay, if I know d theta dt, what's ds dt? Well, if d theta dt is some constant, omega radians per second or whatever, I can ask how fast is the spot moving along the wall. And so I've got, know this rate, I'm asked for that rate, find a relationship between s and theta. Well, that's just trig. The tangent of theta is s over d. Implicitly differentiate with respect to t. And I got secant squared theta d theta dt equals 1 over d ds dt. Plug in the omega for d theta dt. And where is it? And solve for ds dt. So there we go. And what I see is that as theta heads to pi over 2, I know something about the secant. Of course, secant's reciprocal of cosine. And so if the cosine is headed to 0, the reciprocal is headed to infinity. The secant would be heading to infinity. And the cosine is 0 at pi over 2. And so this will head to infinity when theta heads to pi over 2. So as this angle theta is getting close to pi over 2, so essentially parallel to the wall, that this dot has to go infinitely fast, which means it would have to go faster than the speed of light. And how could it go faster than the speed of light? This time it actually is a little spot of light. Right? And so clearly this is not what's actually happening. What is actually happening, right? Does that spot of light move along the wall? Clearly it can't go faster than the speed of light. So what's happening? What does it do? But I also, in trying to analyze it, I realized that maybe that light isn't actually, the spot on the wall, maybe it isn't actually growing in length. It might be staying the same. There was a long time where I just couldn't tell. I couldn't figure out whether it really was growing like our intuition says it should, or if it was staying the same as it moved out, or whether it was shrinking in size, literally getting smaller as it went out. And then, of course, there's questions like, does it matter whether I'm doing the conical light source or the cylindrical light source? Does it matter whether the light is spreading out or whether it's parallel? Do I get different results? Certainly, I don't think I would expect to get different results in the rate at which the thing is moving, but I might expect to get different results in whether the size of the spot is growing or not growing. So let's take a look at some of the things that I tried. So first of all, we're going to look at a spray of photons. So my thought here is, my face is always in the way. Let's turn this on and you'll get an idea of what I'm doing here. So I just want to look at a bunch of photons being shot out of this thing. So don't worry about the shape of what's happening, just a single laser being shot out, a bunch of photons right in a row just being shot out in different directions. And you can see this spinning around. You can see it looks a lot like you'd expect, except that there seems to be a bend to the light now, because light doesn't travel infinitely fast. It is slower than that. And so what I really want to do is I want to slow light way down, right? So in this animation, what's happening is each one of these dots is sent out, and then it moves along a straight line at whatever the speed of light is that I'm setting for it. At the moment, I have it set at 6.4, and this would be slower and slower. But you can see that the beam is bent. In fact, if I move over and zoom out enough, you might even see that beam is bent so far that it's hitting the wall in two places. In two places. That is, the light that is first emitted, that is, if I start with it looking in this direction here, off to the right, that first photon, watch it come out, right? That first photon comes out, and it's moving along, and it never will hit the wall. That next photon is going up at a slight angle, and then here. And there seems to be a spot where there's essentially first contact. That the spot doesn't come zooming in from infinity. It starts at a point and then goes in both directions outward. This was quite a shock to me. I'm sure that other people know this. I mean, I don't feel like I'm doing anything new, but I never really thought about what was going on. I certainly felt an uneasiness of that spot coming in from infinity, but it doesn't come in from infinity. It goes out to infinity. So this moves in both directions. And then when you're aimed down here, of course, there's no, I'm not bothering to draw the photons when it's down here. These are headed out. This headed that way, this headed that way, and now you got two spots that are headed in both directions at speeds that approach the speed of light. That is, how do I want to say this? That this point gets moving faster and faster and faster, but it only moves as fast as the light moves. And because it's at a little bit of an angle, it's a little bit less than the speed of light. But in the limit, it's moving parallel to that and at the speed of light. So, so off that goes out to infinity. So now that we have that, we've got this idea of this first point of contact, and then it splits off. Let me do some other things. This spray of arcs is a similar thing, but as I move it now, how do I move this? Actually, I'm going to do it this way. You can see that what I'm doing is, rather than just a single photon, I'm saying let's do a cone, right? This is the first type of searchlight that we had, and as you move out, it's getting wider and wider. Now, what we think is happening, right? What we generally think of is this, that all that light is just heading off in a straight direction, and it moves so fast that it's not doing that. But it isn't doing that. The stuff that was aimed one way is still headed that way, and then as the light turns, you're spraying the light off into different directions. So each one of these arcs is light that was emitted at the same time, and it's all headed in the same direction. And each of those arcs will get wider and wider as they move outward. And as I increase time here, you can see that this spreads out. You can see that initial contact, the point on the wall, gets bigger. I should point out that light is only between the red and blue curves. Everything out here is dark. Then the spot on the wall gets really big, and then it splits into two spots, this one here and that one there, and they both head off in their own directions towards plus and minus infinity. And the thing that I see as it keeps going out and out and out and out, well, I can't if I don't zoom out to it, the light is only between the red and the blue curves, and here's the spot on the wall. Is the spot on the wall getting big, longer and longer and longer? The answer is no, it does not. It only gets as long as the distance between the red and the blue curves. And that can be calculated in that the red curve is the leading edge and the blue curve is the trailing edge, so that in any direction, the amount of light that's traveling in that direction is, you can say, well, it takes so much time for the red curve to get there, and then from the red curve to the blue curve, that much time is times the speed of light is the distance of light in that direction, and the spot on the wall will never grow bigger than that. It will only get as big as this direction here, and as the light gets further and further away, it's traveling essentially parallel to this line, and you get that length as the limiting width. Now, one of the things that I've done here is, again, this is what actually happens. This is what we think is happening. Let me pull alpha. Let me pull the time back here. Right. That is, at any point in time, pay no attention to the stuff in the upper left there. It's aimed this way, and we think, oh, it's being sent that way, but it's not. when you slow light down, it's not all going off in that direction. It's back over here. I put this in for two reasons. One is I wanted to be able to see that there is this conical effect, that each of these arcs is a little bit bigger as it moves out. So I can line them all up there, or I can wrap them back around as to what's actually happening. So in this case, the spot moves along the wall. It doesn't come screaming in from infinity, right? There's a point of initial contact, and then it gets longer, and then it splits into two and moves in both directions. And both of those will reach a limiting length on the wall equal to the radial distance between the red and the blue curves. With the parallel light, this is kind of a fun one too. This was actually kind of a pain to analyze at first. This is what I thought was going to be, right? But this is the way I thought I was going to be able to do it, and I couldn't. The thing is, I'm trying to figure out at any time, can I tell where the spot on the wall is? And that turns out to be tricky to do, because you got to take the amount of time that you have to turn so far through an angle, and then you have to travel along that. You have to travel along that path to get out to the wall, and so you got to add up. So you got to do the time of both to figure out where X is, and it's tricky. And with this type of system, with the parallel lines, lights being shot off. Let me say, this is what we think is happening, that the light's just being shot off all like this, but it's not. It's back over here because the light travels in a straight line, and the stuff that was shot that way keeps going that way. But you can see these are all the same length, and then I roll them back to where they were. I view this like a deck of cards being sheared, but it's not only being sheared, it's being sheared and twisted. And so you see each card moving off in its own direction. And again, you'll have this point of first contact where the light first hits the wall. That point is then going to grow to a point, there, and then it's going to split into two and head off in both directions. Now I'm going to add a few more in here just to get a better idea of what's going on. There we go. I got a few more lines in there now. Let me zoom out and watch what happens as I increase time here. Watch the size of the spot on the wall. Whoops, with this many, the animation is pretty slow. So, okay, here we go. Increase time. What happens to that spot on the wall? What happens to that spot on the wall? Does it get bigger? Does it get smaller? It gets smaller. That is, each one of these line segments is the width. The length of that line segment was the width of my searchlight. But this certainly is less light on the wall than it was than that width. And in the end, you will be looking at what's going on down here, where everything is parallel, and they will just get closer and closer to parallel. Whoops, move that out. What happened to it? Moved off here, right? And that just gets skinnier and skinnier. You can see it on the other end is probably better because, well, the other end's been traveling longer, so it's further away, right? So we get up to here, and you can see that the spot on that side of the wall gets really small. Now, this is kind of a crazy thing because I look at the stuff that's happening over here. So this is the backwards side, and with the spot on the wall moving off in that other direction, it's like if you were standing on the wall, if you were over here, would you think that the light was spinning in the other direction? Because as time increases, it's moving this way along? Maybe, right? If you had sensors along the wall and saw, hey, this spot got lit, oh, this spot got lit, this spot got lit, you'd say, hey, the searchlight's headed that way. But then if you had other sensors that could measure the age of that light, the light that hits further out here is older, right? It got sent out first. So as you're moving this way, you're actually watching this. It feels like it's going the other way, but you're watching it backwards in time. It's going, you're getting newer light sooner and older light later. Just fascinating. Let's go back and do a little bit of calculus here. One of the things is we notice the point of first contact. I should be able to calculate that because that is, after all, a max-min problem, right? I want to find the spot on the wall that minimizes the amount of time to get there. And so what I'm going to do is I'm going to look at this. I'm going to say this. I'm going to set this up like this. I tried this several different ways, and I made mistakes many times. I kept making the same mistake, and it wasn't lining up with what my animations were showing. But so I'm going to show you both ways that I calculated this, finally doing it correctly. So I want to calculate the time it takes to get to this spot on the wall. Okay. So at this spot on the wall, there's going to be an angle theta here. And so what has to happen is we need to turn through that angle and then travel this distance. Okay. So if omega is the angular speed, then the amount of time it takes is theta divided by omega to turn through that angle. A couple of things here. I'm measuring positive thetas in the counterclockwise direction, and for some reason I'm measuring positive s to the left. Whatever. Then the distance traveled here, well, the distance traveled, if d is the distance between the lighthouse and the wall, then d times the secant of theta would be the length of that hypotenuse. So if I take that distance and divide it by the speed of light, then that would be the time it takes to traverse from here to there. So the total time is the time turning plus the time traveling. Okay? And what I want to do is I want to find the value of theta that minimizes t. Okay? And so what I can do is I can just say, well, that's classic max-min problem. Take a derivative, set it equal to 0. Another calc 1. Here we go. So the derivative of t with respect to theta is 1 over omega plus d over c secant theta tan theta. This is minimized when this derivative is equal to 0. And so set this equal to 0 and solve. The problem is it's tricky to solve with the theta in the secant here and the tangent. So hey, this is a Calc 1 class. Let's use Newton's method. All right, so I'm going to say here's my function. Take its derivative with respect to theta. And for this example, I'm just going to use c equals 3, omega equals 1, and d equals 2, which I believe, if I do my spray of photons here, let me see. If I put c at 3, I know this is off the screen for you people watching the video. The wall's 2 units away, and the angular speed is 1. And so when I look at where is that point of first contact, it seems to be right about there. I would say it's right around 2, right? Somewhere close to 2. When I do this, so that was the x value was close to 2. I'm calculating theta at the moment. But anyway, I'm going to make my initial guess be -1. I'm expecting, looking at this picture, I'm expecting it to be behind, right? That this is on the back side, that point of first contact. I called it 2 there, but that had x is positive on the right side. This has s is positive on the left side, so I'm expecting negatives here. Anyway, plug that in to the Newton's method formula. I get my second guess is that. I plug that in. I get this, I get this, I get theta is about negative 0.80489701118 radians. I can then figure out what s is, because s is going to be d times the tangent of theta. And so I plug that in, and why do I have it as 2 times the tangent of theta? Oh, because d was 2. Right, d times the tangent of theta. In this problem, d is 2, and you multiply by that, and you get negative 2.079, which is pretty close to where we thought it was going to be. Okay, let's double check this in a different way. In this case, I'm turning around, so x is positive to the right. I'm also going to measure theta from the horizontal upwards in a counterclockwise sense. D is still the distance between where the lighthouse is and perpendicular distance to the wall there. Again, I'm going to try to minimize the time, but this time as a function of x, not as a function of theta. Right? And so still it's the time turning plus the distance plus the time traveling. Time turning is still theta over omega. The distance now, I can use Pythagoras to get that hypotenuse there being square root of x squared plus d squared. Divide that by the speed of light to get the time it takes to traverse that. And I get that the total time is this. I'm going to replace theta as a function of x because the tangent of theta is x over d. So theta is inverse tangent of d over x. Did I say x over d? D over x is that. So now I have t, the time traveled, as a function of x. What I was always trying to do when I first analyzed this was to find x as a function of t. And that proved difficult. It's essentially take this equation right here and solve for x. X is got inside this arctan and x is inside that square root. And that is particularly tricky to solve. But in this max-min problem, I don't need to solve that. I need to solve the derivative of that's equal to 0. So let's take the derivative. And we get dt dx is, derivative of arctan, chain rule, derivative of this thing, there's a 1/2 times that thing to the negative half power, but then the chain rule gives the derivative of the inside, and so that's 2x, and the 2 from the half and the 2 from the 2x cancel out. Anyway, we get that. Distribute this x squared in through here. It cancels out that x squared that's in the denominator, puts an x squared right there. Anyway, it looks like this. And I need that to equal 0. I set that equal to 0. And now this actually turns into a fourth degree polynomial in x. Fourth degree polynomial equation in x. In fact, better than that, it's quadratic in x squared. Okay. Now, before I do this, one of the things I had to do was to square both sides. So I'm running the risk of introducing extraneous solutions. And so I go back to this original equation and I realize that everything on the left-hand side here is positive. And so everything on the right-hand side is positive except potentially that x. And so I know x has got to be a positive. Now remember, in this example, positive was in the direction we expected to be off to the right. And I keep doing this, which looks off to the left, off to the right. Anyway. So I set this up, quadratic formula, the opposite of b, plus or minus, the square root of b squared minus 4ac all over 2a. The plus or minus, I don't have to worry about the minus. I know I'm going to have to take a square root of it. And if this is negative and that negative, I'm not going to be, it's going to be negative. I'm going to get imaginary numbers and that's not what I want. So this has to be a plus sign. And then when I take the square root of that, I have to use the positive square root. I can simplify this in a sense. I can pull a d squared out of here as a d. So there's a d over 2. I distributed the half in there. Anyway, and you've got this. Now, I like this in that this is negative d squared over 2, and this is d over 2, and this is at least as big as d, right? Because this is a square root of d squared, which should be d. So, and then you're going to add something positive to it. You can see that as the speed of light gets bigger, that you're going to be adding more onto this, and it's going to be moving. It's going to be getting bigger and bigger values of x, and as the speed of light gets smaller, we're getting smaller values of x. In this case, in our example, with d equals 2, omega equals 1, and c equals 3, we get that x equals 2.07955, which is the same answer we got before, and it corresponds to what we expected. So we went from related rate problems to, we used some Newton's method here, we did a max-min problem, all to figure out what's going on. But one of the things that occurs to me, feeling better about the spotlight problem, is that I originally started with the snowflake problem. And the snowflake problem was the stuff screaming in from infinity. It wasn't the other side. It was my intuition of I don't really like what's going on there. Didn't feel right. It wasn't right. It definitely was something different. And so it's like, well, okay, what's actually happening with the snowflake. So here's an analysis of the snowflake. What I have here is this the orange is the street light, the purple is the snowflake, and all these little dots are shadows waiting to be cast. And as I increase this, you can see that first shadow is never actually going to make it down to the ground. It's headed off this way. Each one of these dots is the shadow being cast at a particular time, and they move along. They move along their line until they hit the ground. This orange dot that's coming screaming in here, this is the idealized shadow that we thought we had of just drawing the straight line down there, right? So when we thought the shadow was supposed to be there, it hasn't even hit the ground yet. The shadow is still on its way to the ground. Shadows can't travel any faster than the speed of light. So again, there's that point of first contact, and then it chases it in, and by the time the snowflake hits the ground, everything's lined up, and the idealized shadow, well, I mean, at that point, you didn't have to travel very far, right? When the snowflake's barely off the ground, the speed of light becomes less relevant. Okay. So I like watching that, in that the actual shadow lags behind the idealized shadow. This is where we thought it should be if there was just infinitely fast light, but it falls behind there. But again, there's this, the shadow actually is moving in both directions, because there's that point of first contact, and the shadow goes both ways. As the light is here, if I back out here, that shadow is still moving along the ground in the other direction. In the other direction. If you were standing over here and you watched that shadow move whoop, across the ground, would you think, dang, that looks like the shadow, like the snowflake's going up? Wouldn't it look like the snowflake's going up? But you're seeing the light in reverse order. You're seeing time backwards in that direction. And so the shadow is not going up, it's going down. Yeah. But then it occurred to me too that, so here we are on the ground. What about the balloon problem? Is the balloon problem just the snowflake problem backwards? Is this what happens to the shadow of the balloon? There's no way this could be what happens to the shadow of the balloon. There's no way that shadow is going to jump ahead of the ideal shadow. And is it going to just do this? Sorry, where am I? I want to see this happen. Is this going to just, is the shadow just going to vanish? It's like, no. Running time backwards is not the same as the reverse problem. Time is not symmetric forward and backwards. So let me turn on this. No, not that. Let me turn on where? Oh, let me go here. So let's look at this one. Now this one is set up. Whoops, it's not set up from the start. This one's set up so that as I move time forward, these are shadows waiting to be cast by that as it's rising. Right. Again, the orange dot is the idealized shadow. Each one of these dots is moving along a line, the straight line at the speed of light, whatever I have it set at. And you can see that the shadow is lagging behind the idealized one. And this will just, head on up. And when the snowflake or when the balloon is above the light, the shadows are headed upwards. But still, we got shadows waiting to hit the ground. They were cast. And all from this one, they're all waiting to hit the ground over there, and they will eventually do it. That's a very different picture than what was happening when it was falling. In fact, I can look at both of them at the same time and say, here's the snowflake falling. You should be looking at the red shadows. And here's the snowflake rising. You should be looking at the multicolored shadows. Fascinating stuff. Fascinating stuff. And I think, do we really care? I mean, from the point of view of us, shining flashlights on the wall or whatever, the speed of light is so fast it doesn't matter. But we live in a universe of colossal size. And we are constantly looking into our telescopes and seeing things that are millions, billions of light years away. So if you got something like a pulsar sitting out there somewhere, spinning around, sending gamma rays out every once in a while, we get this burst of gamma rays. And here it is off in the infinite, let's say this is the plane of our solar system, and you got a gamma ray burst that's coming in from way over here at this it's almost in the plane of our solar system, and it hits, Mars, and then it comes across and it hits, the sun's here, and it hits Jupiter, and then it goes out and hits some other planet like Pluto out there. How do we know if we're seeing forward in time or backward in time? Because is it spinning this way, or is it spinning that way? Are we on the trailing edge where we've got that phantom? It's not a phantom, but that backwards moving thing, or are we on the forward moving side? I don't know how to tell the difference. It's phenomenal. Anyway, thanks for putting up with me and listening. Again, here's all my information. If you have any questions, please feel free to contact me.